여러분 안녕하세요. This is the second video for chapter 7. So in part 2, we are going to talk about the secondary factors on diffusion, which we didn't consider in part 1. So in part 1, we obtained several analytical solutions when we had a clear and certain boundary and initial conditions. However, if the analytical solutions cannot be obtained due to the secondary factors and others, we need to use the numerical solutions instead. So we are going to see how we can, what kind of numerical solutions we can use. And we are going to talk about the macroscopic effects and also the atomic scale or microscopic secondary factors. So numerical solutions. So what we want to do is basically solving these diffusion equations, which we talked about in part 1, such as Fick's law. But they can solve analytically only if the initial and boundary conditions are simple. So in general, you cannot obtain the analytical solutions. So you have to solve the problem numerically. So how to solve them numerically? That's the question we want to answer. So we are going to use a different modeling in here. So this is the medium. The figure is the medium. And then we are dividing this into a different regions. And the thickness of each region is delta x. And you can see that the amount of atoms in that region is N0, N1, N2, and so forth. So each region will have the average concentration, which will be given by this. And this is average because if delta x is bigger than 0, right, it has a finite thickness. So the concentration might change within the same region. So this is the average. And then we are basically assuming that these atoms, any atoms in certain region can move to its neighboring region for a short time period. So if you wait for delta t, let's say this is kind of small enough, the time is small enough, so you don't skip, you cannot go to the next neighboring region, but you have enough time to go to neighboring region within a short time delta t. And then this is kind of a random behavior. It will be 50%, it's going to be 50 to 50, right, to the left and right. There's no dependence on the direction. And we can define a certain frequency for this to happen, which will be given by this equation. So it has a temperature, large temperature dependence. So anyway, if you assume this, if you calculate the flux between two neighboring regions, the flux will be given by this equation. And then as you already know, if you make the delta x fairly small, this will be same as this Fick's first law. So what this tells us is that, right, if you also use this relationship from the top, if you combine these two, what you get is the relationship between the diffusivity and this Debye frequency, and this thickness matters as well. But anyway, what we actually want to know is how much does it change? What's the new concentration after time delta t? And this is the equation you can use. Or if you change this to a actual volume concentration, you can divide the whole thing by delta x. You will get a something like this, right? So you are replacing the Debye frequency with D and the equation from here, from the above. So anyway, so this is what you do in your numerical modeling, right? So the numerical model will give you the concentration for each region, and then you can define a short delta time, delta t, and then you can calculate the new concentration for each region using this numerical method, which you can solve definitely. And then you go to the next time. You do another delta t and calculate this. So one thing you need to realize is that, as you can see from this equation, this delta x and delta t is very important, right? So for example, in here, what we are assuming is that the concentration is relatively uniform within the delta x, which means for this to be accurate, for this numerical calculation to be accurate, you need to make delta x really small or small enough. And also, this concentration is changing with time, right? So if your delta t is really large, um, this is not constant during that delta t. So this equation also breaks down. So delta t also needs to be small enough. Both delta x and delta t should be small enough. So one thing we want to know is how small should they be? And this type of mathematical manipulation kind of gives you some clue. So if you choose delta x and delta t such that this thing is 0.5, what you get is this equation. So now you can completely cancel the CI term. So this is kind of extreme case or case at the boundary, because if this is actually larger than 0.5, what you're going to get is you will get some minus CI term, which means it's kind of oscillating, because the new term is negative of the original term with some additional values from neighbors. But this is kind of doesn't make sense at all, right? So you can see that whatever value you use for delta t and delta x, it has to be smaller than 0.5. So anyway, if you choose a delta x and delta t to be small enough, you can use this method and find the diffusion behavior in your simulations. So we are gonna see secondary effects, macroscopic secondary effects. So the first one we want to see is electric field effects. So what we typically do is that, so when things are doped, when there's a doping gradient, right? So basically, this is the doping concentrations. So what happens is that you have the electric field when you have this gradient in the doping concentration. So there will be the E fields in the semiconductor. And this E field actually changes the diffusivity for a dopant. So this E field can enhance the diffusion. And this is the kind of model we typically use. So you can see that it's almost the same. This part is the same, but you add this correction term, which is H, and H approximately can be represented like this, where the C is the concentration, right? That's what's diffusing, and the Ni is the intrinsic doping concentration. So where this comes from, so we are going to see that on the next page. But before going there, this is kind of simulation results, which shows the electric field effect. So the color in here is the doping concentration of the boron, the concentration of the boron. And then if there's no electric field effect, so there is electric field because you have junctions. You have some electric fields in here because it has a junction in here. But if you account this electric field dependence of diffusivity in your simulation, you don't see that the electric field doesn't seem to have any effect because you don't see the difference between here and here. So no electric field in here and some electric field in large electric field in here, and you don't see any difference in the boron concentration. But if you include this electric field effect for diffusion, now you can see that because of this electric field, they really suck out the boron in this region. So you can see that the boron is kind of depleted in this region. What this tells us is that you should include the electric field effect. This is not small. This can be pretty large enough and then give you really big difference. So this is something important to consider. So again, where this He comes from. So this is the derivation. So when we talk about the flux of the dopants, there's a regular dopant diffusion term, which we already talked about in the previous chapter, but there could be some electric field enhanced term. So if we have this additional term that we didn't discuss before, right? The Fick's second law should also change. It should also have the secondary term as well. So we want to know this term. So the unknown thing is this velocity of the dopants, and if this is due to the electric field, there should be some mobility multiplied by the electric field, and then the electric field is generated by the doping gradient. So by finding derivative of this thing, which has the doping concentration, you can find the electric field. So basically combining these, you can calculate the velocity as a function of doping concentration. And then also, this is the famous relationship between the mobility and diffusivity. So if you replace this mobility with D, this is what you get at the end. So you can plug this thing into here, and what you get is this, or this, the same thing. These two things are the same thing. And then using these relationships, you can kind of find the approximate value for this new flux, which has the electric field term. And it turns out that you can approximate the above equation with using H, where H is represented by this one. So if you closely examine this H term, what you realize is that this H is always smaller than 2 or equal. So for example, if C is infinite or much larger than Ni, this term will become 1. So its maximum value will be 2. So this figure kind of shows you the electric field effects. This is the simulation results. So this is the arsenic, N-type dopant is arsenic. So it was like this before the diffusion, but after diffusion it became like this, which looks pretty normal. But for P-type, which is boron, it's low doping concentration. Initially it's uniform, it's flat. Initially it's flat. So even after diffusion, they should stay flat, right? But as you can see, after certain time, after the annealing, it looks like it diffused like this. And that's because you have junction here between the N-type region and P-type region. And there will be an electric field which creates diffusion like this. And another macroscopic secondary effect is concentration dependent diffusivity. So what's shown here is basically um, so the boron concentration after diffusion. So if you model D to be constant, if it's not a function of the doping concentration itself, this is what you would get. So depending on whether your initial dose is large or small, you will get this or this. But if you model your D to be a function of the concentration, so basically as you dope more, diffusivity goes up pretty high. So when the concentration is low, uh, this doesn't play much role, right? Because for example, if N is when the doping concentration is low, N will be similar to Ni anyway, right? So even if you use these models, the D will still not change. So with this different model for D, they stay the same. But when you have a high doping concentration, the N will be actually larger than Ni, or even much larger than Ni. So if you use these type of models where the diffusivity depends on the electron concentration, you will get much faster diffusion at higher concentrations. So you will get this box-like profile after the diffusion. So it's really fast in high doping concentration, but it slows down quite rapidly. So that's why you have this sharp drop um, in your doping profile. So anyway, if your diffusivity is a function of concentration or X, right? You cannot take this out of this derivative in X. So you have to maintain this in here. So can we actually measure the diffusivity as a function of doping concentration or C in general? So we want to know whether we can find experimental measure the diffusivity as a function of concentration. And one experimental way to measure it is using the isotopes. So you want to measure the diffusivity of the boron as a function of boron concentration. Um, so what you typically do is you use B11 in the background. So let's say this is X and this is a concentration C, and your background is kind of flat. So this is B11 background doping concentration. And for B10, you maybe ion implant a small amount. So this is like log scale. And maybe it's like here. So this is for B10. And you let them diffuse. So B10 will diffuse. And this is much smaller than the B11. So the overall, the concentration for B11 plus B10 will be still just like this, which is flat. So it's going to be maintained like this flat. So your background concentration is not changing, but this B10 concentration will change with time if you anneal the sample. So by changing the concentration of B11 up and down, you can measure the diffusivity of B10 as a function of the background concentration. So by doing these measurements, you can measure the diffusivity as a function of concentration. So what's the actual equation for this, right? So if you do this type of measurements and what was founding, that's on the next page. And these are the equations people use to model. So for N-type dopants, they depend on the concentration of the electrons, like these. For P-type, they depend on the concentration of the holes, And these terms also changes with temperature. They are function of temperature. So this is the relationship, uh, this diffusivity coefficients and the temperature. And then there is another constant, d0, and the kind of activation energy term. So these are the table which shows all the values you can use for different impurities in silicon for this diffusivity. So using these values, you can actually calculate the diffusivity as a function of concentration and temperature. So at the end, if you include this E-field dependence and concentration dependence, you will get, in the simulation, you will get this type of strange behavior after diffusion, right? Two like humps, and then kind of a weird angles, slopes, and there's some kind of peaks. And all these strange effects can be explained using what we just discussed, the electric field and concentration dependent diffusivity. Another thing we want to consider is the segregation. So we already talked about the segregation in chapter 3, right? So you might already remember this uh, equation where we used. So here the segregation is basically at the interface between oxide and silicon. And you can see that for different dopants, you will get different segregation behavior. And you can see that for arsenic and phosphorus, they want to stay in the silicon. That's why you see these peaks in the silicon. But for boron, they get depleted in silicon and goes into the oxide. So they like oxide. So when this balance is broken, you will get some flux between the oxide and silicon through the interface in here. So this is the actual flux. But after the equilibrium, this flux can be 0. So in your flux equation, you have this K0, which is the segregation factor um, for different materials. But that needs to be multiplied by H to calculate the flux, and H is the interface transfer coefficient. So this is kind of equation which kind of leads to this one we saw before. Uh, so there will be two fluxes, right? Between the oxide and silicon, there will be flux going to the right, going to the left. So you need to find the difference between those two. And then in steady state, that should be small, 0. So what that means, this should be the 0. And so it should be this. And we know that due to the segregation, it should be the K0, right? So you can rewrite this equation using K0 and another variable called H. So what's the typical K0 value? Again, boron likes the oxide, but for everything else, they like silicon. So boron will segregate into the oxide, but phosphorus and others will pile up in the silicon. So the next question is, can we actually measure the segregation effect? And as we discussed before, if you use the SIMS, you can measure the segregation, but the oxide has to be pretty thick because the SIMS doesn't have a really good spatial resolution. So if it's too thin, you are not sure whether the measurement data is from the actually oxide or it's the oxide plus silicon. So for thick oxide, you can use the SIMS to figure out the segregation effect. But for thin oxides, it's better to use the threshold voltage measurements or even the CV measurements. So it's less direct than SIMS, But for thin oxides, these are the kind of only method you can use to characterize the segregation effect. So there's something called interfacial dopant pileup. So this is similar to segregation, but not exactly the same. So this picture is kind of um, good picture to show you the difference between the interfacial dopant pileup and the segregation. So the idea is there is some kind of layer which is not a oxide and not a silicon, because you cannot have a really abrupt interface between the oxide and silicon. You will have some interfacial layer which kind of mixes oxide and silicon. Um, so this layer will have some different property when it comes to the dopant concentrations. So what we are saying here is this interfacial layer happens to consume a lot of dopants like this. So you have to ignore this interfacial layer to um, model the segregation. The segregation is between this point and this point, right? So ignore the interfacial layer. But you also need to be really precise, you need to account for this interfacial layer, which has a quite large dopant concentration, but this is pretty thin. It's very thin, so the amount of dopants might not be that large, but the dopant concentration can be pretty large. So that's a interfacial dopant pileup. So we talked about macroscopic diffusion. So the first law basically um, we are assuming the diffusivity is kind of constant, um, and that's valid when the concentration is low or the difference or the concentration gradient is low. But we want to include the secondary effects. So the diffusivity will depend on the concentration and the E field. Um, so that's the importance of the secondary effects. That's why we discussed it. And we talked about this oxidation enhanced diffusion, right, in the oxidation chapter. But this macroscopic effect doesn't really explain these effects like OED. So we have to use the atomic model or microscopic model. So that's what we are going to discuss on next few slides. So again, the motivation is there are many effects on diffusion which cannot be explained by macroscopic model. So we need to use the atomistic view for diffusion. And even for the diffusion, one thing we realize is that the vacancy and the interstitials or interstitial C can play an important role for diffusion. So basically, the diffusion will be faster if you have vacancies and interstitials. So for example, let's say this is the dopant. For this to move to another region, so that's the diffusion. If there is a vacancy, it's much easier for this thing to move to another lattice site. Um, so if you don't have the vacancy in here, let's say there is a silicon in here, this dopant has no place to move. So it's very difficult for this to diffuse, but if you have the vacancy in here, they can move pretty well. So it's almost like they are kind of a pair of dopant A and the vacancy. And this pair of vacancy and the dopant atom can move faster than just the dopant atom without the vacancy. So this is called vacancy assisted mechanism. And similar thing can happen with the interstitials. So the difference between the interstitial and the interstitial C, if you remember the previous chapter, right? Interstitial is just the interstitial. It's not paired with anything, but interstitial C is a pair of two atoms which is competing for the same lattice sites. But so they are not that different, but you see the difference between those two. So if you have the interstitial silicon atom, they can kick out the dopant. So if there's no interstitial, the dopant is just happy in here. So there's no motivation for this dopant to move around or diffuse. But silicon comes in and then kicks this dopant out, and then the diffusion of this dopant will be initiated by this kick out. So interstitial can cause the diffusion to happen, or maybe this atom, dopant atom, also formed a kind of pair with the interstitials, right? So they were kind of competing for the same lattice sites, but they end up kicking out these dopant atoms, and then this pair will be broken, and then maybe this dopant should kick out another silicon in the neighborhood. So whether it's just interstitial or interstitial C, it's not that different, but both of them can assist diffusion of the dopant. So what we are trying to get to is higher vacancy or higher interstitial cause higher diffusion, more diffusion, faster diffusion. So how do you actually model it? So we talked about this already in oxidation, right? So oxidation, you are doing oxidation in here. It generates a lot of interstitials, and then this diffusion is enhanced. But in here, it's not oxidized because it's covered with a nitride. So not that much interstitials. So you will just get a regular diffusion in here. Another one is something called oxidation-induced stacking faults, right? So this is faults, and these faults will grow with higher interstitials. And you can see that with the oxidation, the stacking faults grows faster. So anyway, this is the typical equation we use to find a new diffusivity as a function of the concentration of the interstitials and vacancies. It's pretty simple. And these are the typical values for these coefficients Fi and Fv. And you can see that for boron and phosphorus, it doesn't have the term which depends on the vacancy concentration. This is 0. And for antimony, it's close to 0. So what happens is that with the oxidation, which increases the Ci, it will enhance the diffusion for boron and phosphorus. But for antimony, it's most likely to be retarded, because as the Ci goes up due to the oxidation, the Cv will come down because I and V can recombine with each other. So Cv is decreasing, and antimony has really large Fv, which is close to 1. So it's going to be retarded, most likely retarded. And arsenic, it's kind of a half and half. So it's likely to be OED if this condition is met. One thing to keep in mind is that this is 1. Can you guess why? You can pause and maybe think about it. So the answer is if Ci and Cv is equal to its equilibrium value, right? This should be 1. So this should be 1, right? So what you get is dA star Fi Fv, and this should be the same as dA star, because that's when the interstitial and vacancies are in equilibrium. So which means this should be 1. So what's the actual value, like typical value for this ratio, right? The concentration of interstitials over the equilibrium concentration. So they can change with a different oxidation method because the concentration of the interstitials will be proportional to the square root of the oxidation rate. Um, so um, um, so that's why you get a higher concentration for the wet oxidation than the dry oxidation at the same temperature. But it does have also the temperature dependence as well. So it's actually coming down with the temperature. So this doesn't show you the temp dependence on temperature, but you can see that this value is pretty high, right? The typical values are 1110 for typical oxidation temperatures around here. So this oxidation effect on the diffusion can be pretty large because these values can be pretty large. So again, this is another example, right? For example, for boron, this is no oxidation. This is with the oxidation. You can see that faster diffusion, so oxidation enhanced diffusion for boron, but for antimony, it's the opposite, oxidation retarded diffusion. And we can see that due to the oxidation, right, this ratio for interstitials, it's higher than 1, but the vacancy is smaller than 1. So using the equation that we described, you can actually calculate the diffusivity, and you can check whether it's enhanced or retarded. So this is another example, right? We already looked at the antimony, but there is arsenic too, right? So with the arsenic, it's enhanced as well. So again, using this equation and Fi and F3 values we use, in the table, you can check whether it's enhanced or retarded. So to summarize the entire chapter summary, doping is important for making transistors, and they have to electrically active. That's the reason why we dope the silicon. And doping concentration important, and the shape of the profile, whether it's like smooth or abrupt, that's also very important for device performance. And we use ion implantation to dope, but after that we do a lot of annealing and then let them diffuse. And we are going to look at the ion implantation itself in chapter 8, next chapter. And when you want to understand this atomistic diffusion, you need to understand the interaction between the dopant atoms and vacancies and interstitials. So diffusivities are generally proportional to defect concentration, which we have seen in the model. And also the temperature is very important, and there are other important factors which we talked about before, the Fermi level and so forth, and like oxidation. So that kind of explain a lot of secondary effects we see on diffusivity using this atomistic diffusion model. And we used a lot of simulation tools to calculate the doping profile after semiconductor processing. And we looked at some of the equations we can use in the simulation at the beginning of this video. So that's it for the entire chapter 7. So if you have any question, please let me know, and talk to you next time.